Just remember what a logic gate is like. The logic gate, the output of the logic gate depends on what is on the inputs of the logic gate. So I have here, for example, a Nand gate, and the Nand gate has two inputs, A and B. It can actually have, you can have a 4-input NAND or an 8-input NAND or whatever, but this is a 2-input NAND gate, and the output is just called Q. And the NAND function is, as we've discussed before, is the not AND function, where AND means that the output is high only if both of the inputs are high, if input A and input B is high. So the NAND gate is the output is not high only if both of the inputs are high. So the truth table for the NAND gate is this one, right? The truth table has the inputs A and B, and the output is Q. So the inputs are A and B. We can have, since they're binary inputs, they can only be zeros or ones, so the only combinations are 1, 0, 0, 1, 0, 0, and 1, 1. The not AND function has an output of only if both of the inputs are 1, then the AND output would be high, so the not AND output would be low. So that means that otherwise the not AND output is high. So 1, 0 has an output of 1, 0, 1 has an output of 1, 0, 0 has an output of 1, 1, 1 has an output of 0. That's the NAND truth table. So that's just a reminder of combinatorial logic. And so now we've got sequential logic. So this is sequential logic. Sequential logic depends both on what's on the inputs, but also what was on the inputs, or what was on the output after the last input. So sequential logic depends on what was on the input. This particular latch is this particular piece of logic or memory bit is called the SRLatch because it's got a set and a reset input. As an output, is still got just the output, which is called Q. For various reasons, all of these chips also have an output called not Q. It's just the opposite of Q. So you don't need to know what not Q is. It's always going to be the opposite of Q. So we don't really have to include that in the truth table, but I'm going to go ahead and include that in the truth table just to be clear that we've got the S input, the R input, the Q output, and the not Q output. So we've got the inputs and the outputs. And the possible inputs, of course, are still 1, 0, 0, 1, 0, 0, and 1, 1. Now here's the function of an SRLatch. An SRLatch remembers what was on the output before. So in order to, I got to make this a little neater. In order to denote an input and a previous input and a next input, we talked about the nth input. So if the nth input is 1, 0, then the output is going to be sorry. Let me start with 1, 1. Let me start with the bottom, 1, 1. So what the purpose of an SRLatch is, 1, 1 says remember what your last output was. So what the output of 1, 1 is just going to say, hey, stay the same. Remember what the output was before, Qn minus 1, the previous step. So then this would just be not Qn minus 1. 0, 0, let me now start at the top. So what a 1 and a 1 input on set and reset says is just, hey, remember what it was before, don't change your state. Keep your state, okay? Then I think it's going to be clear then what set and reset do. What set does is it sets the output to be 0, and what reset does is it resets the output to be 0. So it sets the output to be 1, sorry. So what set does, if set is 1 and reset is 0, then that's setting the output to be 0. And what reset does, if set is 0 and reset is 1, then the output is 1. 0, and so that's basically a single memory bit. It'll remember its state. You can either set its state with the first two combinations, or you can tell it to remember its state. So you don't need any more functions. So what's 0, 0? 0, 0 is actually an indeterminate state. If you put 0, 0 in, you don't know what the output of the latch is going to be. It's an indeterminate state. So you really only want a 1 on one of the inputs. You never want both zeros. Okay. How do we build an SRLatch? An SRLatch is a very simple thing to build. You can just make it out of 2 NAND gates. And what you do is you take the output of one NAND gate and you put it as the input of one of the other NAND gate and the output of that NAND gate, and you make it the input, one of the inputs of the first NAND gate. And then the 2 inputs left over are the S and the R. And let's see how that works. So what I have on the right here is simply the truth table of the NAND gate, so that we can see how this SRLatch works. Let's just start with an indeterminate state. Indeterminate in the sense that when we're starting, before we start using the SRLatch, let's say we don't know what the output is. So if we don't know, and what I mean by that is we don't know what Q is. So we don't know what Q is, but let's just say, oh, we could always measure it, but if Q equals 0, let's see what happens. If Q equals 0, therefore, if we input an S and an R as 1, 1, that means we're putting a 1 in on the S, we're putting a 1 in on the R, and we're saying if Q equals 0. And let's see what the output, what is going to output. Well, that 0 goes in as an input to the bottom NAND gate. And so what we have in the bottom NAND gate is a 0, 1. And so the output of a 0, 1 NAND is 0, 1 is a 1. So there's a 1 there, which is the opposite of 0, so that makes sense. That 1 gets to be the input here, but Q naught, by the way, is just the output of the bottom gate. It's not the output of the bottom gate, it's the output of the bottom gate. We're just calling it Q naught. Okay, so that 1 is the input to the top gate. So on the top gate, we've got a 1, 1 and a 1, 1 on a NAND gate, right? That has a 0 output, 0. So what does a 1, 1 do? A 1, 1 makes it keep its state. So therefore, Q remains 0. It keeps its state. What if, when we started, Q was equal to 1? If Q equals 1, and therefore if we input an SR of 1, 1, so let me start that again. If Q is a 1, and we input an SR of 1, 1. So if Q is 1, then Q naught is 0. Let's see if that makes sense. So we got a 1, and then that goes, so I'm tracing that down. Let's do a different color. The 1 goes in here, and so I've got a 1, 1. Let me pause a second. Let's start again. Okay, if Q equals 1, and that means Q naught must equal 0, if that's the starting state. And if we input a 1, 1, let's see what we get. Then this 1 goes down here, and we got a 1, 1, and a 1, 1 on the NAND gate truth table gives me a 0 output. Great. A 0 in here, a 0, 1 on the NAND truth table gives me a 1 output, and the state remains the same. So therefore, Q remains 1. Check, check. Okay, so 1, 1 makes Q remember state, whatever its state is. Okay, let's try something else. Again, and say, okay, if Q equals 0, and let's just try putting something else in. Let's say SR, the SR state I put in is a 1, 0. So I put a 1 in here, I put a 0 in here, and again, if Q is 0, then I've got a 0, 0 here, and a 0, 0 in the truth table for a NAND gate gives me a 1, that 1 up here, a 1, 1 at the top, a 1, 1 gives me a 0. So if Q is 0 and I put in a 1, 0 in SR, Q remains 0. Okay. What if Q is 1 and I put in an SR of, if Q equals 1 and I put in an SR of 1, 0. Let's do that state and then we'll move. So let's just say if Q starts as 1 and that means Q naught is 0 and I put in a 1, 0 on S and R. So now let's take this 1, that 1 gets put in here. So we got a 1, 0, a 1, 0 on the NAND table gives me a 1 as an output. So it changes this output to be 1. That 1 goes up here and now we've got a 1, 1, a 1, 1 on the NAND table gives me a 0, so that changes this output to be a 0. So if Q equals 1, so now we're looking at this bottom one. If Q started out as 1 and I put in an SR of 1, 0, it changes the output state to Q equals 0. Check. That is what an SR latch is supposed to do. So now let's go ahead and write down what we know about the truth table. With the first two examples, that an SR of 1, 1 just keeps Q as whatever it was before we put that 1, 1 in. So whatever Qn is, it's whatever it was before. And then we showed that if SR is equal to 1, 0, that's the first line in my truth table, then it's going to set the output Q to be 0. And then we can go ahead and you can go ahead and do the same thing to figure out the other two parts of the truth table. And what you'll find is that, and I'll leave it as an exercise to you, you'll find that there's a 1 here and that this is an indeterminate state. And what I mean by that is that it's not going to make sense what the output is. So therefore, it's unclear electronically what it'll read. Okay, so there you go. That's an SR latch.